then we said that this linear elastic theory is, I'm going to say here, the most accurate method, if you like to use it, the most accurate analytical method. It's not really used when it comes to actual design. So in practice, people don't really use it. You guys see my screen, right?
Yes, sir.
Yes.
Yes. Mariana, are you in? So this method here is kind of the most accurate method, but it's not really used in actual practice when it comes to design. So as you understand here, once you start to put pressure, you're going to have here, pressure is going to be coming this way, if you like. And if you don't have enough vertical reinforcement, to bring this together, like ties like this, it's going to open up. Therefore, you should expect that you're going to have here some tension force. From this performance, you're going to say, well, you're going to have here some tension force coming this way and some tension force coming this way. After this L transfer, which means a transfer length, after this distance, the stress is going to be uniform throughout the entire depth of the beam. Uniform meaning not equal, but it's going to look like this. So at this distance, the stress distribution is going to look like this. This side is going to be compression and this side is going to be tension. And this makes sense because at the end of the day, you're going to have a force coming this way and a force coming to the other direction. And this moment here, created by or developed by this stress distribution, is going to be equal to the same moment developed at the face of the block or the beam. So if you have tension here, I'm expecting that I'm going to have also some compression force at this location. As if I'm going to have here compression block, very similar to the conventional concrete design, and here I'm going to have here some tension forces. So here's distribution at distance of LT, which is roughly the same as the depth of the beam. It's going to be here compression, it's going to be tension. And throughout a section, if I'm going to be cutting a section here at this crack location, we have Oscar in. Oscar?
Yes.
All right. Very good. Thank you.
Welcome. Thank you.
So as I said just in this slide here, that I'm going to have two forces. One force here is going to be tension and the other force here is going to be compression. So whatever moment that you apply through here, right, by putting this force right in this place, it's going to resolve it into a couple. It's going to be equal to this tension or compression multiplied by the distance between the C to the T. The distance from T to C is going to be equal to L transfer, or H, if you like H, subtracting X. So I'm going to say here, if I'm able to find out the moment at this location, in the vertical direction, this moment, if I take it here, is going to be equal to C or T multiplied by the distance. This distance is going to be equal to H subtracting X. Like what you see here in this equation. Therefore, the tension force is going to be equal to the maximum moment divided by H minus X. Now I need to understand what is this maximum moment, where it's coming from, and how can I develop this moment diagram. So I'm going to say I have here two sets of forces. The first set of force is going to be only one point load, which is this PI. The other force, which is going to be opposite to it, is going to be this stress distribution. And this is going to be composed of two forces. One of them is going to be compression. The other one is going to be in tension. It's going to be like this. This force PI is going to be equal to this tension or this compression subtracting this tension. Because at the end of the day, summation of the force in the X direction is going to be equal to 0. Now, if you imagine that you're going to be taking here some sections horizontal sections. I'm going to say here's the first section. I'm going to be taking it here. And this is going to be right above the bottom. So I'm going to say I'm going to go maybe above the bottom, maybe a couple of inches or just 1 inch. Once you take the section here, and then you can do also integration for the forces, for the stresses. Just take this stress block, if you like, this stress block. Find out this resultant force right in the middle of it. Now, take the moment about this point, about this surface CD. So the only force that I have is going to be this force, right? Because I'm going to be taking the moment right here at this section. So you look down. It's going to be this little force multiplied by 1/2 of the height that I have considered. And this is going to be the first moment right here that I'm able to develop. So I'm going to say, let me bring this up. I understand that the moment is going to be going up, but here's the maximum point. And this makes sense. If I'm going to be taking the moment here, I can do integration for this section, and it's going to be this stress distribution from these 2 points, which means it's going to be this trapezoidal distribution of stress. Resolve it into one force and find out the location of this centroid. Now take the moment arm from the section of interest to the force. So you take this force, multiply by this distance, it's going to give the moment at this location, which is the maximum moment in this direction here. So now I understand. I have this trapezoidal. I'm going to be taking this into little bit of segments or sections, very small sections when it comes to the height. I'm going to have lots of forces, small, very small forces. Take the moment about this section. It's going to give you this value here, which is going to be this moment. I'm going to call this here M1. Now, once it starts here to move up, because you'd like to see here what happens, right at this point here, the moment is going to be equal to 0. Look at the moment here diagram is going to be equal to 0. At this point, this moment developed by this trapezoidal, if you like, if you take this moment developed by this trapezoidal stress distribution, it's going to be equal to this concentrated force, which is this Pi multiplied by the distance to the force itself. So the moment coming from this side is going to be equal to the moment coming from that side is going to be equal to 0. They're going to be equal to each other. Now we're going to start to move up. Once you get here, a certain point, and that certain point right there, you're going to have the maximum moment. And if I don't mind here, if you don't mind, I'm going to call this to be the positive moment, maximum positive moment. So take this stress distribution as one big point load multiplied by the moment R, subtracting, if you like, this point load multiplied by this distance from here to there. It's going to give you the maximum moment on the other side. And this is going to be right at the crack. You see this vertical crack is going to be right there. It's going to be the maximum moment ever that you can develop throughout the depth of this beam section. So if you want this tension force, because this moment here along this direction is going to be balanced with the moment on the horizontal direction. So these two couples is going to be balancing each other out. So if you take the moment here from the vertical section and say it's going to be equal to the moment at this horizontal section, therefore C or T multiplied by H minus X, this is going to be here H minus X, H subtracting X, is going to be equal to this M max. So if we are able to develop this stress distribution, which we should be able to, because we have done this at the beginning of this course, we were able to find out the stress distribution at any point. So if you have this stress distribution and you start to develop the moment diagram for it, like an Excel spreadsheet or so, and you should be able to draw this, take the maximum value and know the exact height at which this moment is going to be occurring. This is going to be right there. This is going to be the maximum tension force that you're going to be able to develop in the vertical direction. And then you said this M max is going to be equal to T multiplied by H minus X. With that, you're going to have the maximum tension force. You take this tension force, you divide by 20 KSI. Why 20 KSI? This is going to be the limit for the steel. And then with that, you're going to have the total cross-section area that you'd like to provide in the vertical direction. We're going to see an example on how this is going to get done, but this is going to be the basic idea for it. So as I'm saying here, here's the tension force, maximum moment divided by H minus X, and total cross-section area for the ties is going to be equal to this tension force divided by F sub S, and F sub S is going to be equal to the 20 KSI. Why 20 KSI? Because we'd like to limit the amount of cracks that you're going to see there. Now, there's some load factors. Don't forget, we're going to end up with some design. So the load factor is going to be 1.2 for this force. And the anchored stress level, F sub P, is going to be 80% of FPU. I'm going to show you exactly what the ACI code requires when it comes to this stress that you're going to be designing for. So what the ACI says, in many cases, you're going to have this small local zones, because if you're going to have more than one set of strands, you're going to have this local zones. And all of these local zones, they're going to be forming the big, you can see here, general zone or global zone, if you like. It's going to be this section here. So this H is going to be the same as this H. So this is going to be equal to the total depth of this beam. And within this local zones, we should be able to provide some spirals around the strands. But when it comes to the big zone, I should be able to put big ties. So here's the stratum tie method that we have discussed also. You're going to have here the stress is not going to be really a 1-point load, because most likely you're going to have a small plate, and the small plate is going to be right here. This is going to be like bearing plate for the anchorage. This is why the stress here, or the force, is not just 1-point load. It's going to be actually distributed over a little section. This is why you cannot just call it to be P. It's going to be P over 2 and P over 2. You're going to split it. Why? Because this plate, it has a dimension in the Y direction. Eventually, if this is going to be in the center, at certain point, you're going to have here 2 equal points. And you can simply say that if this box here has a height of roughly 50% of the beam, here's the other box, and this point load is going to be at the quarter point, which means from here to there is going to be 1/4 of an H. From P over 2 to P over 2 is going to be 1/2 of H. P over 2 to the top is going to be 1/4 of an H. And if you are able here to draw this diagram, and then you're going to start here to break down the force, it's going to be like here, it's going to be inclined force to come closer to this P over 2 at H over 2. You should be able to find out this force C and C, and therefore also this tension force, and then you can put the ties right there. It's going to be around this point. More details on how this is designed and what happens if you have some eccentricity, that this strut is going to have different angle from that strut, and the amount of force that you're going to have here is going to be a little bit different from the amount of force that you're going to have at the bottom. Now, this is the approximate method which is included in the code, in the ACI code. And if you're doing a design, this is going to be the method that you're going to be using. So we have here again 3 methods. We have the elastic linear method, which is kind of more theoretical. It is good for analysis, but it is not good for actual design in practice. And then we have the stratum time model. And the stratum time model is used in design when you have complicated beam end. But if you have a simple case, like the case that here that you're looking at, it's going to be 1-point load. And you understand that this point load is going to be only at the end of the beam. And the plate over which you're going to be applying this force is going to be called edge of the anchor. This is not going to be equal to a 0, like nothing. It's not going to be 1/4 of an inch. It's going to be most likely 4 inches to 5 inches. And usually you're going to have this point load is going to be kind of eccentric. In some cases, it's going to be right in the middle, which means this eccentricity of the anchor sometimes going to be equal to 0. In some cases, it's going to have some value, 3, 4 inches, 5 inches. It depends on the design. Once you have all of these parameters, you should be able to come up here with some solution. And the solution is going to be very simple. Look at this equation. It says here, the tension force, this is going to be T for the bursting force, and it's going to be going up in both directions. This tension force is going to be equal to 25% of the total load coming here at the anchor. In many cases, you have many strands or a few strands, and they're all set on the same bearing plate. So if this is the case, you just add them up all together. So you're going to be taking here 25% of the total force coming on the anchor. And then you have this multiplier here. This multiplier is to reduce the total bursting force due to the fact that this point load is not really acting on a zero distance, that it has a depth of this edge of the anchor. So we take this edge anchor divided by h. So let's say if this is going to be here 24 inch for the total depth of the beam, and edge of the anchor is going to be what? Let's say 4 inches. So you take here 4 divided by 24, it's going to be 1/6. So you're going to have 7 sectors, 5 sectors. So you're talking about roughly, how much is this? Can someone help me with this? If we assume here that we have 1 minus 4 divided by 24, how much is that?
It's going to be 0.83.
What?
It's going to be 0.83.
All right, good. So as you see here, there's some 17% reduction because of this factor, because of the depth of the plate. So if you like to ignore the depth of the plate, this is fine. Don't take any reduction. You can just take 1 multiplied by 25% of the total force. So the worst case here that I'm going to put reinforcing is going to be equal to 25%, right? The reinforcing is going to be resisting 25% of this point load. If you put bigger plate, you're going to be having some reduction here in this bursting force. Now the question is, let's say I came up with 6 number 3. So I'm going to put here 6 number 3. I'm going to put here 6 vertical ties. Where should I center them about, right? Because I need to center them about something. So where is this location? So if I'm planning here to put 3 bars, it's going to be, let's say here's going to be 3 bars. Here's 1, 2, 3. And I have here all the rebars. Now I need to center them about this location. So I'm going to put them right here. So the question is, where is this D bursting? It's given here. I have some empirical formula for it. It's given by this equation. It says it's going to be 1/2 of total depth of the beam edge, subtracting 2 times the eccentricity of the anchor. So let's say eccentricity of the anchor could be maybe 4 inches. So it's going to be 8 inches. So you're going to have here 24 minus 8 inch. You take half of this, and this is where you're going to draw a line, and then you start to put the ties right and left of that location. Meaning that you're expecting the biggest force to be right here at this location. This is here the ACI method, and as you see here, it's so simple. They made it really very simple compared to this method. The linear elastic theory. This is going to take some time before you're done with it. Any questions before I move to the following slide set, 9.3?
Yes, Professor.
Yes.
For that formula on the slide 22 that you just showed,
Yes.
the D burst is only the one in the middle, right? Not the one on the left.
What do you mean the left?
I see two D burst.
Oh,
So
it's the same. It's
oh,
gonna
it's
be
the same thing,
almost
right?
the same.
Okay.
Yeah, it just happened that if you're going to be taking, just imagine that you're doing here this line and this line. Usually in analysis, this is going to be almost the same. So you know that this D burst is going to be almost the same as this. And I can tell you the reason. Look at this. Look at the equation. 1/2 of H minus, which means 1/2 of H minus what? E anchor. So where's 1/2 of H? Let's say here's 1/2 of H, right? 1/2 of H minus 1/2 times 2, which means minus E anchorage, right? The eccentricity of the anchor. And here's the eccentricity of the anchor. The distance from here to there, right? So this is going to be exactly the same as this deep burst, right? Does it make sense now or no?
Yes.
Okay. So it just happened to be the same. When you look at this equation here, 1/2 of H, okay? Here's 1/2 of H. From here to there. Let me write it down. This give you 0.5 of H. Right? And then you subtract the eccentricity. And here's eccentricity from here to there. So this is going to be the bursting depth. It's going to be the same as here. Right? Let's move here to the next slide set. So here's what I have in the third one. We're going to have some examples, solved examples, how this is going to get done. Same equation that we're just looking at, right? This is going to be the simple method, the approximate method. And most likely this is going to be the method that we want to use. Okay? You're going to be taking your 25% of the total force, and then you have this reduction factor, and the location is going to be right at this location. This is going to be the depth for the bursting. Here's again the equation and then definition of everything that you have in here. Now, this is going to be the force is going to be sub pre-stress ultimate, which means I need to factor this. And if you recall, we said the factor is going to be equal to 1.2. And here's the definition for the eccentricity, for the H, and the whole thing. Also, don't forget that you have this pre-stress force most likely is given an angle, right? And this angle, it means that you're going to have here two resultants, two components. Here's one component for the force, and here's the other component. And this component should not be ignored. And as it says here, you need to add this factor. If this angle is significant angle, it means that this force, which is this component here, is going to be significant, and it needs to be added to 25% of this axial load. So if you like, you can take 25% of this horizontal component, take 25% of the horizontal component, and then you add to it summation of the force multiplied by sine of alpha. If this alpha is really a big angle. Otherwise, if you want to, you can ignore this angle and just use the total force, whether you have an angle or not. So if this angle is going to be very small, just use the total force applied in this direction, in this inclined direction. Don't use the horizontal component in this case. All right, now let's see what the code says about what force that I need to use when it comes to my design. It says that your force is going to be the smallest of all of the three. So it's going to be the least of, and then you have three options here. Here's the load factor, 1.2. Again, load factor, 1.2. Same load factor here. Look at this, 1.2. So you're going to have the load factor multiplied by one of the three, the smallest of the three. And this is going to be the stress that you need to design for. And this is going to be APS, which means the cross-section area of the strains. Okay, the strains. And the third one, it says the maximum jacking force designated by the supplier. Because in many cases, you can have this value for your design, but the maximum force that the supplier or the pre-stressing company is going to be a little bit smaller. Or the pre-stressing company is going to put more force, knowing that some loss is going to happen. So they say, you don't really need to design for this, which is most likely the case. Precasters, they'd like to put a little bit more force. And if they're going to put here a little bit more force, the issue is you don't really need to design for it. You just need to design to 94% of the yield strength for the strands or 80% of FPU. This will be the level of force. This two usually would yield the same value, 216, 216. This is going to be like the stress in KSI. Multiply here by 1.2 is going to be 259 KSI 0.2 times APS. And this is going to be the design force that you need to use in your analysis. This is going to be the fee factor that we need to use in our analysis. It's going to be 0.85. And let's see what does mean by doing design here. The first thing that you need to be sure of, you need to be sure that the bearing stress right on the beam is going to be within the capacity of the concrete. The bearing stress itself, F sub B, is going to be equal to that force that you just calculated here. Right? You take this force, which is P sub PU, the pre-stress ultimate force. You take this and then divide by the bearing plate size. You're going to have this FB. So the bearing stress is going to be equal to P sub PU, or just sub U, divided by the effective bearing area, which means the final net area of the bearing plate on the concrete. This stress here, you want to keep it within the following. 70% of FCI prime. What's FCI prime? Anyone remembers the FCI prime? Compressive concrete stress, right, at the time of transfer. Multiplied by square root of A divided by AG. I don't know if you guys have taken structural steel, some steel courses. You design the bearing plate for the steel plate on the concrete. It's going to be the same thing. This A divided by AG. AG, the AG is going to be the cross section area of, if you see it here, of the bearing plate. And A, we're going to see an example of this. Simply, I can show you this for quick. You know that the stresses is going to distributed in this way. It's going to have a kind of an angle, right? At a certain point, I'm going to be taking here a section and then compare this AG. So AG is going to be here, the cross section area of the bearing plate on the concrete. And at this depth here, I'm going to have the effective area, which is called here A. So when you take here A divided by AG, this value is going to be more than 1. And then you have a maximum of this component, the square root of A divided by AG. This max is going to be equal to 2.0. So you have a limit here for this bearing stress. So the bearing stress is a section in the code, and it has certain fee factor, as you see it here. And it has certain way of doing it, is how you determine this A compared to AG is given the bearing section. We have this example, which is the same example we have used in the past for the girder design. Same parameters, same values. Total depth is going to be 40 inches. Concrete strength is going to be here 5,000 psi, and FPU is going to be 270. And if you remember that we use 13 strengths in this beam here. So here are the 13 strengths. We're going to put them here on through rows. The first row here is going to include 5 strengths. It's going to be at 2.5 inch from the bottom. If you look at this, you're going to have here 5 strengths. And the second row is giving additional 5 strands. The third row, row number 3, is giving only 3 strands. So you have total here of 13. If you take the force here, multiply 3 or 5 or 5, you're going to end up with 198 and then in a fraction kips. And here's the location, 4.5 inch, 4.5 inch. Now, someone has came up with this design, which is in the textbook, and they decide here that they're going to put here in 3 rows with this distribution. Now the question is, how much is the total force? Total force is going to be the total force for all 13 strands. And the other question is, where is this at? Measured from the bottom of the beam. How much is this? To the resultant. So to do this, you can just take the centroid, take the moment of all of the 3 forces at the bottom of the beam. So take the 198 multiplied by 2.5 plus 198 multiplied by 7 inch plus 198, the 118 multiplied by 11.5. And this is exactly what we have here. And then you divide this by what? You divide by 198 plus 198 plus 118. And instead of using the 198, 198, and 118, you can just say, I'm going to have here 5 strands. So here I have 5 strands. Here's the 5 strands at the bottom. Another 5 strands. And then 3 more strands. So instead of taking the force, I can just say 5 times, because it's going to be 5 times some F, some force, plus 5 times, again, plus 3 times. And then at the end, I'm going to divide it by the total number of strands, the 13. With that, this location from the bottom is going to be at 6.35 inches. And this is exactly what it says here. The location of all this resultant force is going to be at 6.35 inch from the bottom of the beam. Any question?
How are those numbers calculated? The 118,000, 198,000? Is it just like random?
Not the random. This is the force. This is based on this force. If you remember in the code, the way that we have done it, which means this force is here, it's going to be based on that.
Okay, thank you.
No problem. So this is going to be the final design forces for each group or for each row. Now, we'd like to solve this first by the linear elastic stress. Just to entertain the idea of using this method and finding out the moment, right? So how this can get done? So first, it's going to be about the linear elastic stress method. So number 1, I need to do the stress distribution at d distance or h distance away from the face of the beam. So now I know that the total force is going to be right here at 6.35 inch according to what I have done here. This gives you the location of the force, the centroid of the force, because I'm going to have 5 strands at the bottom, 5 strands in the middle, and 3 strands on the top. So I ended with 13 strands at a distance of 6.35. Exactly what I have. Here's the centroid. The centroid is going to be 18.84. Therefore, the eccentricity that I have is going to be equal to 1884, subtracting 635 is going to be 1294. This is going to be the eccentricity, E. With this E and with the properties of this section as given here, I should be able to find out the stress distribution. So here's the stress distribution. We did the equation that we used to. On the top is going to be 409 psi. It's going to be in tension. On the bottom is going to be 2250 psi as in compression. Now I have this distribution of stresses. So I decided here to cut this stress distribution into sections. Each section is going to have the height of it is going to be equal to 4 inches. So we're going to say here's the first section. So here's the distance from the bottom, from 0 to 4, 4 to 8, to 12 to 16, 20, all the way to 40. How many sections do I have now? Roughly, I'm going to say maybe about 10. Maybe a little bit over 10, because when it comes here, maybe I need to have more sections. And then I'm going to start here to do my integration to find out the force. So here's the first one, first segment. It's going to be this one here, this force from here to there. How can you find out this force by integration? You say, first, let me find out the stress at this point. You see here, here's the stress here, is going to be 2250. And now I need to find the stress here, which is 2117. So where is this 2117? It's going to be the stress at this point. Where is it? 1051? It's going to be the stress at this point. Same thing, same thing, same thing. To find out here the average stress, you say 2117 plus 2250 divided by 2, right? And with that, you're going to give you the average stress. You multiply here by the width of the beam, because you need also to look at the beam and the cross-section area of it, because you're doing integration. Integration means you find out the volume of this stress block over this beam. So you're going to be taking this stress here, convert it into very small forces at 4 inch on center. The total force coming here, the applied force, gave you 376 kips, roughly 376 kips. And now you can start to find out this moment diagram. Here it says divide this into 4 inch increments and find out the forces. Now let's look here at the table. So here's the location for the moment plane, the distance from the bottom is going to be 0 to 4 inch, 6.35. This is going to be a critical point. That's why we're going to stop at it. And 6.35, which means right here. So I'd like to take the moment at this location. And then 8 inch, 12, 16, 20. So this is going to be the 4 inch interval. The section width here, I'm going to be taking from the beam cross section. Look at this, 18, 18, 13.3, 10, 6 inches, and then again 18. Why is that? Now let's look here at the beam section. So the bottom is 18, 18, and then comes a smaller, and then 6 inches, and then it goes back to 18 inch. So to find out the width of the section. So each one of this section is going to have a width and a depth. And the depth is going to be the typical 4 inches. So as it says here, the stress at this D minus 2 inches, right? This is going to be the location at which I was able to find out the stress to be 2250. How do you do this? You do it by interpolation. And then after that, you start to multiply it by the cross-section area over which that you are applying this. You take the stress here, multiply by 4 inches, multiply by the width. You take this, multiply by 4 inches, multiply by the width. And with that, you're going to have this concrete force. And the concrete force is going to be like this yellow force. After that, you start to take the moment only for the P force. So this gave you the moment for the P force. So the way it works, when you cut a section, you look at the bottom only, you don't look at the top. So you say, okay, let me cut the section right here. Do I have any force or any moment here for this force? Don't forget, I'm going to be cutting this section, look only at the bottom. Now I have 2 columns. One column is going to give me the moment for this P load, and the other column is going to give me the moment for this little forces, the concrete resistance. When you cut the section here, you look down, you don't see this force yet. And this is the reason that if you look here at this table, you're going to see here 3 zeros. Why? Because you have here 3 sections. The first one's going to be right at the bottom, the second one's going to be here, and the third one's going to be at 6.35. So 0, 4, 6.35. For all of this 3 sections, when you cut the section, look down, take the moment for this P load, you're going to see that there is no moment. And this explains the first 3 zeros. Now, once you go up for each interval or segment, you take the moment for this P force, and this gives you like negative moment if you like. You see here it's going to start to grow up. Once you get to 40 inches, this distance is going to be equal to 40 inches, subtracting 6.35 multiplied by this force, and it's going to get you this moment here at the bottom. And don't forget the number here is small because it says here inch pound times 10 to the 6. The second column here, or the following column, is given for the concrete resistance moment. And at the bottom, when you cut the section right here, there is no forces below it. But once you go at 4 inches, you're going to be taking one force, which is this force here, multiplied by 2 inches. And this explains at the bottom, there is no moment. And once you start to go up, positive moment is grown up. The net moment is going to be this moment that we are looking here at. So this moment is going to be the net moment. It's going to be equal to this moment from the stress distribution, subtracting the moment from this point load at the end. So okay, here's the net moment, the difference between the two. Now where's the maximum moment? Let me look. Here's the maximum moment, 0.75. Do I have another moment? So where's this 0.75? Oh, this 0.75 is going to be right here. And the maximum moment for the spalling is going to be the 0.2. Where's the 0.2 here? Let me see. It's going to be this negative moment. All right. So I have here two moment values. I should be able to use this 0.2, which is this negative moment. Here they called it negative. But if you like, some people would like to call this to be the negative and it's going to be the positive, which is absolutely fine. Positive and negative here doesn't apply, like the same way that we're doing beams, and then we say if the tension at the bottom of the beam is going to be positive, this rule here, it doesn't really apply. So here's some examples. How do you determine the moment at certain sections? So the moment at section 4, when you are at 4 inches, is going to be equal to this force, or this stress, multiplied by the cross-section area, times 2 inches, which is a moment arm, right? So they give you here how you're able to determine the moment through certain steps. So this is going to be like examples. At 8 inches, how would you do the moment? So forth. Now we understand from this that we're going to have one section is going to be bursting force and the other section is going to be spalling force. So the question is, how much is this X force? Now, because we're going to be using this maximum moment, right? Let's give you the maximum moment, which is a 0.2. And you have another moment here, which is a 0.75. So you have here two moments that you may call here to be the maximum moment. It's going to be 0.75. Another moment here is going to be 0.2. The question is, which moment should I use? The 0.75 or this one here, 0.2? So we're going to say, if you like to find out the bursting stresses and forces, you need to use this moment. The spalling, excuse me. If you like to find out the bursting stresses and forces, you need to use a 0.75. If you like to be very detailed, you can come here and put some ties, right? Based on this analysis, based on the 0.75 moment. And then based on the spalling, you're going to be using this 0.2 times 10 to the 6 pound-inch for the moment. And based on this, you're going to have here some reinforcing. Now, for simplicity, since you're going to be doing here construction, you'd like to use one of these ties. And this gives you the tie that you'd like to use. So someone's going to say here, why don't you just use this big moment and just use it for the entire depth of the beam? Since you're going to have the same tie running for the total depth of the beam. You said, okay, let's take here the 0.75 times 10 to the 6. Now, this X distance, usually it is used as 1/3 of the height. So we're going to say approximately is going to be equal to, let's say, about 15 inches. And with that, I'm going to have 30 kips as a tension force for the bursting force. You say, okay, now let me take the 30 kips, divide by 20 KSI to limit the cracks. I need here 1.5 square inches of reinforcing to be provided in the vertical direction. This reinforcing should be enough to cover the spalling forces, because the spalling force here is going to be based on the 0.2 times 10 to the 6 moment, which means it's going to be based on this value here. And here we go. Look at this number here. Look at the 1.5 square inches. 1.5 square inches is what is needed. This is based on this calculation here. You're going to be using here number 3 ties. Each tie is going to have 2 legs. So just imagine, here's the beam, and here's the tie. Of course, the beam doesn't look exactly like rectangular section, but you're going to have a tie. And each tie is going to have 2 legs with total cross-section area of 0.22 square inches. So the question is, how many ties that I need to provide? Here, you're going to provide some ties, right? Vertical ties. It's going to be like this. And the question is, how many rebars that you want to put at the end? So if you take 1.5 square inches, you divide this by 0.22, you end up with nearly 7. You need to have here 7 stirrups or 7 ties, 7 vertical ties, not just 2 or 3. Now try the spooling. The spooling here is based the 0.2 square, the 0.2 pound inch to 10 to the 6. Do exactly the same analysis. You're going to end up with cross-section area of 0.4 square inches. And this 0.4 means that you need only 2 ties for the spooling. But for the bursting, you need 7 bars, 7 ties. Now, which one would you use? I'm going to say, well, definitely you need to use 7 bars. With that, we are done with this method, the elastic linear analysis method. Any questions on that? Yes?
So for the spalling, we would use 2 number 3 stirrups, right?
Well, I need here 7. And once I put them, I need to take them all the way up. I cannot just end them up here, right?
Okay.
So if you have a tie here, let me be sure that from the same page on this. Here's one tie that I'd like to put. Here I need here, I'm gonna say I need 7, number 3. I did same analysis for the spooling, and the rebars I need in this location is gonna be 3, 2, number 3, right? So here I need here 2, number 3.
Got it. Thank you.
So if you like to end, no problem. If you like to end this rebar like this and put 2 here, this is fine. But in this case, you need to put some horizontal rebars. Otherwise, what are you going to be hooking this stirrup or tie about? So you need to have your top bars and bottom bars. So the easiest way, if you just provide this ties, especially it's going to be all number 3, small bars. Just put them for the third depth. Now it means that here you provide 7 and here you provide 7. So you cover the spooling and you cover also the bursting at the same time by putting the same ties. Any other questions?
Yeah, do we know the spacing on those bars?
Okay, very good question. How would I do the spacing if I'm doing here a design? Let me take you back here to this. I put the X distance to be equals. Usually they say it's gonna be 1/3, which means about 15 inch. So let me take you back here. This is where you're gonna put here the reinforcement bars, right? So let's say it's gonna be 15 inches. Now I need to put 7 bars. And this is gonna be here 15 inch. Let me go to this section. This is good. So right here, I'm gonna start to put my first bar. It's gonna be right at 15 inch, right? From the face. How many bars do I need to put right? How many bars do I need to put left? Just for curiosity here. Do I have 7? I'm gonna have 1 in the middle. How many? How many?
I think 3 on each side.
Yeah, 3 and 3. Good. Gonna start here to think. How can I put the 3 bars? I'm gonna put here 3 rebars, right? From the end, I'm gonna leave here 2 inches. So from the first rebar or the center rebar to this rebar is how much? I'm gonna say about 13 inches. How many spaces? I'm gonna say 1, 2, 3. I'm gonna say, well, it seems that maybe 4-inch space is gonna be good. Why? Because I'm gonna end up with 4, 4, and 4. It's gonna be 12, right? And maybe 2 here, right? It's gonna be 14-inch. So it makes sense because I'm trying to put it here to center it about roughly 15 inches. And turned out I'm gonna start here with 2-inch, and then after this 4-inch spaces, I'm gonna end up with exactly 14-inch. Not a bad idea. So I'm gonna say, okay, let me put here the ties to be at 4-inch spaces. So the spacing here is gonna be 4 inches, and we're gonna have here 7 ties. And the starter is gonna happen here at 2 inches from the face of the beam. Make sense? So I'm gonna say the space is gonna be at 4-inch. Now, if this is an actual design, and the total depth here of the beam is 40 inches, are you going to provide only 7 rebars, or do you want to add more? I say, okay, 40 inches. Now where I'm at in terms of the distance, I'm going to say 1, 2, 3, 4, 5, 6. So the total distance, if I may put it there, say total distance equals that I have used already. I'm going to say, I'm going to have here 6 spaces times 4. It's going to be 24. And of course, you have the starter. It's going to be a total of 26 inches from the face. So you can say, should just provide, 7 rebars. So you know what? Since they're going to be at 4 inches, let me add 10 of these. If I add 10 of these, what do you think I'm going to end up with? Here's 1, 2, and 3. They're not that expensive to put number 3 tie. So if I have here 10, it means that I have 9 spaces. So I'm going to say 9 times 4 plus 2. How much is this? 38 inch. This number is good because the total depth here is 40 inches. So I'm trying to come here to the entire end block and put enough ties so that you feel that the entire length, which is the end block here, the entire length, which is equal to the depth, is getting all covered with enough ties. I'm gonna say, how many more ties did I add? It's gonna be only 3, number 3. And the cost of them is gonna be nothing. Just to add 3 more ties. It's gonna be nothing compared to the cost that they are putting here. Other questions? All right. Who wants to take a break?
I think it's a good idea.
Continue or a break?
Can we take a break?
Okay,
Break sounds good.
absolutely. Let's give it 10 minutes. 10 minutes is good?
Yes.
All right.
Yes.
See you in
Thank
10
you.
minutes. All right. So I want here to look at the force. The total force, and there is no factors here, don't forget. It is based on 376. Kips. And look at the force that we were able to develop in the vertical direction. When you look at it, you're talking about 30 kips. So now I want you to think about this. This force, 30 kips, is less than 10% of this force, of the compressive forces. But when you go to approximate method, they say 25%, which is a big difference. So number one, the percentage itself is different. You're talking about 10% to 25%. Number two, when you do the 25% according to the code, you need to have this load factor of 1.2. So the first thing, you're going to multiply the first force by 2.5 times. And on top of that, you're going to be adding 20% more. Just imagine 2.5 multiplied by 1.2. Just expect the type of force that you'll get if you do the approximate method. Now someone's going to say, why don't we use this method here? I'm going to say, well, this kind of theoretical method, you can do it for analysis. And it's okay, I mean, nothing's wrong with it, but if you like to follow the code and do a design, you need to follow the other method, which we're going to be doing right now in a minute from now. So the second method here, we're going to do it, same thing, same problem, everything is going to be the same. You're going to be your 13 strands at 6.35, and the total force, we can figure this out, and the eccentricity is going to be equal to 12.49, but we don't really need to do the stress distribution in this case. Total force here, if I'm going to be using the code values, is going to be the 259.2 KSI. In this case, I'm going to have 198 kips, and then at the end, I'm going to have total of 515 kips. So I have here 500 kips at least. Now, take quarter of it. You're talking about at least like quarter of this is going to be maybe 100 kips compared to 30 kips, the first value that we use in our design. You do here the bearing check. It's going to be a very simple step that you guys can go through it. It's going to be bearing check analysis. And they say here that each one of this strands is going to have a barrel. It's going to be like a barrel. They call this chucks. The chucks or the barrels is going to be provided right between, instead of the plate, is going to be right between the anchor and between the concrete surface itself. And usually it's going to be 2-inch round block or circle or barrel, if you like. You have total bearing area is going to be 178 square inches. Look at the stress that we're talking about. The stress is going to be 2.8, or let's say about 3 KSI. And look at that level. That level is going to be 3.68 KSI. So you should be fine with the bearing check. Now, let's do here the stratum tie analysis. You have 3 forces. You come to this node, and this node, you're going to start here by putting this node at 4.5 inches. Someone's going to say, how come you came up with this 4.5 inch? You're going to say, if you like, you can do it at 3 inches, at 4 inches. So this number is not exact. It is not like a rule that you have to follow. No, you can go 4.5 inch, you can go 4 inches, but usually you'd like to go the same spacing as this guy here, because you'd like to form here a square as much as possible. For example, the total depth of this beam is 40 inches. So the block itself that you're going to put the reinforcing within is going to be also 40 inches. So you try here to form squares, if you like. So here's one of them, right? You're going to be going here 4.5 inches, going to be 4.5 inch. You go to 3 nodes. And then you say, here's the rest of the beam. You need to decide where this force is going to be going. So we decide that this force is going to be completely transferred to this side. And this force, the middle, which means 5 strains, is going to be transferred to the middle. And then 5 strains is going to be transferred. This force is going to transfer here to the bottom flange. It's just an assumption. In reality, this may not be the truth, or the actual distribution of the stresses. Excuse me. So don't forget that this stratum time method is also kind of approximate method. So once you start here to put the force here, second force here, the fourth is getting right there. Now you start to solve this truss. It's going to look like a truss. It's going to be the same as truss analogy. You start to do the force. You're going to be doing here the force, right? You know this angle. You know the slope of this angle, right? You start to do the components of this force. You resolve it into components. And with that, you're going to end up with two tension forces. One of them is going to be 166 kips, and the other was going to be 203 kips. So this is going to be here the stratum time model. The stratum time model would be resulted in 200 kip for this force. If you do the approximate method, if you just take here 25% of this force, it's going to be much less. Just imagine you take here 25% of this. How much is this? 25% of the 515. How much is that? Can someone help me with this?
$128.89.
Say it again, please.
128.89 kips.
Okay. This is provided also. I'm going to be using what? I'm going to be using this. I'm going to consider that H anchor divided by H is going to be equal to 0. No reduction. I just cross this out, right? In my analysis. End up with 129. Let's say 130 kips, roughly. Now, let's look at this method here. When you end up with 200 kips. Wow, this is going to be a lot. Now, let's take here this force and start to put the ties. Let's see how many ties do I need in this case. So I'm going to be taking this 203 kips, right? And let's see for each tie, how much each tie is going to be taken. Each tie here is taken, if you look at this equation, the phi factor for the tension control is going to be 0.9, 60 ksi times 2 times 0.11, because you have here two legs. So each one of this is going to be taken 11.88 kips. Each one of this time. It means at the end that you need 17. In the previous method, in this method here, when we use the linear elastic, we didn't use this equation. We didn't say the strength or the capacity of each tie. Instead, we say, let's just take the force divided by 20 ksi, which is much lower than this. But we ended up with only 7 rebars. And here we end up with 17 rebars. Now imagine the 17 rebars. How would you put them? Now we're talking about the spacing, right? Look at the spacing. How would you put here 17? You have here 13. If you look here, you have 13. And you space them at 2.5. And then you came here and then you start to put 8. Because this 8 is going to be needed for the spalling. The spalling is going to happen in very close distance from the end block. So this can be one distribution. Another distribution that if you like to do it, you can just take this 17 and just provide all the 17 for the entire depth D. And then someone else is going to say, why don't I just put 20? They just make it easy. I'm not going to put 17, I'm going to put here 20. Look at the number provided in this example. They put here 13 plus 8. They put 21 rebars. So 21 ties, vertical ties. And of course, you'd like to have more concentrated ties at this location. And here's the reason. Look at this force here. Most of the stresses and most of the forces, they happen in the first half of the block. So if you really would like to put more ties, you would put it right here. You'd like to put it in this section. Which means this box here, or this area here of the beam, this is where you'd like to put all the rebars, all the vertical ties. And here you can put some, but you don't really need to be heavy when you put the ties here. In my opinion, if I can put here 20 rebars, I'm gonna put them here at spaces of 4 inch in center. So the center here, this is gonna be like 4 inch, 4 inch. So if you see here 20 divided by 4, it's gonna be maybe 5. I'm gonna put here 5 spaces. So I'm gonna do 3, 4, 5. And here I'm gonna put 15 bars. It's gonna be the closely space is gonna be right here. Okay, put 15 bars like this. Now take 20 divided by 15. How much is that? How much is 20 divided by 15? Actually, it's gonna be by 14. Let's see here for the spaces. Let's say take 20 minus 2. By 14. How much is this?
1.29.
I'm gonna say 1/4 inch. They're gonna be very closely spaced because of this big force. Why did I subtract 2? Because you have 2 inches for the cover. So the first tie is gonna be right here, and then after that 1/4 inch, you're gonna see a bar, a bar, a bar. After that, we're gonna make him at 4 inches for the spacing. Any questions? All right. Now we will start with the shear design for beams, pre-stressed beams. I'm sure that you guys understand the difference between flexure failure and shear failure. In flexure failure, if you have some rebars in the middle here, you're going to start here to apply more loads. And if this beam is strong enough in shear, it's going to fail in flexure, which means the crack is going to be right here in the middle. It's going to be going vertically. If the beam is going to be weak in shear, this is the area is going to get failed because the shear force here is going to be max. But if you look at simply supported beam with 2-point load, and you look at the moment diagram, the maximum moment is going to be right in the middle. Here's the beam that fails in shear, and look at the crack direction. It's going to be at nearly 45 degrees. Another picture here for shear failure. And look at the cracks. They say that you put here a point load, you start to apply load, and you just increase it. So this is going to be like incremental increase in the point load applied to this beam. In the middle here, you're going to have the flexure cracks. And once you come here to the end, you're going to see here, that's what you call here diagonal tension or shear cracks. You don't like to see your shear cracks. Flexure cracks are okay, but you don't want to see big flexure cracks. You don't want to see loss of deflection. Now, here's the reason that you're saying that this is going to be like diagonal shear. If you take a stress element, like a very small element of the concrete, and look at the direction of the crack, here's the direction of the crack, right perpendicular to it is going to be the direction of the tension. So we said that we're going to have tension here in this direction, in this what you call here diagonal tension. Here's the stress element. I'm sure that you guys remember this from mechanics of materials. And you remember when you have only shear applied on the stress element, and the shear stress is going to be tau. You can just call it tau because tau xy is going to be the same as tau yx. They are equal to each other. And this is going to be the amount of the strain. The strain is going to be this angle, gamma sub xy. This gamma is going to be the shear strain. When it comes to resistance of the shear, very similar to what we have done when we have the stress and the strain. We're going to have also the shear stress and the shear strain, but as you see here that we don't see here the yield plateau. Even in the steel, you don't see here yield when it comes to the steel. It's going to be very small, unlike the tension test. Here's the relationship between the stress, shear stress and shear strain. We call this tau, we call this gamma. And the slope of this line here in the elastic range, we call it G, and G is going to be the shear modulus. Very similar to what we have in the tension test. So in tension test, We don't have that. In tension test, what we have the stress, we put F, and then we say is going to be equal to, and then we say is going to be equal to E, the mass elasticity multiplied by the strain E. It should be absent, but you cannot write absent here with this keyboard. So very similar to it. So G is going to be like the shear modulus, while E is going to be the elastic modulus, if you like, for tension test, and this is going to be for shear test. For the steel, we understand that E sub S, which means the modulus of elasticity, is equal to 29,000 KSI. And for the shear, is going to be 11,000 KSI. Here's a stress element that you'd like to take out of this beam and see what's happening there. So right there, if you take the stress element, you're going to see the shear force is going to be coming from the left, because the big reaction is going to be right here. So the shear direction is going to be like this, and from the other side of the element, the shear stress is going to be coming down. And if you have vertical shear, you have this conjugate horizontal shear that goes with it. And if you like to prove this to yourself, you just cross this out. You say, let's say that I don't have here horizontal shear, I have just vertical shear. And as this element is going to be stable, you start to take the moment about this point. You take this force or stress, it's going to keep cancel out when you take the moment about this point. So you have only one stress, which means this vertical stress times this distance. And it needs to be balanced. And the only way to balance it when you have this conjugate shear. So this kind of, if you try here to prove it to yourself that whether I really have horizontal shear or I don't, this gives you the proof of it. That you really need to have this conjugate shear to be able to balance and have equilibrium and stability for this stress element. When you look at this shear direction, you're going to have here vertical one, and here you're going to have horizontal one. The component is going to be like a force coming this way, which is a diagonal tension, which means I'm expecting that I'm going to have a force here in this direction, which is going to be the diagonal tension. And this way you need to put reinforcing. So if you can put reinforcing in this direction, this is great. Otherwise, you start to put vertical reinforcing here to take this component of the diagonal tension. So look at this. This gives you here the stress element that we were just talking about. And here's the direction of the crank. Usually tension force is going to be perpendicular to the crank direction. As you see here, it's going to be going in that direction. So since it is going to be kind of tough to put the reinforcing bars on an angle, just easier if you can provide the ties. And this ties is going to be able to take this component of the force. So let's say if the force component is going to be coming in this direction here, and then you start to put ties, it means this tie is going to be taking this component of this force. So I'm going to say, how about the other component, which is coming this way? You're going to say, what's going to happen for them? I'm going to say, well, you have top rebars, you have bottom rebars, and this stresses is going to be much less the flexure stresses in this case. And the beam should be fine. Right, principal stresses and maximum. I don't know if you guys remember this principal stresses and more circle. Just quick review for it. I'm not going to spend time here, but I put it there for your reference. Let's give you the principal stress, and then you have a couple of equations for it to give you sigma 1, sigma 2. Sigma 1, sigma 2 is going to be the maximum tensile stresses and compressive stresses that you're going to have within the stress element. And this kind of explanation why the maximum stress is going to happen at an angle of 45 degrees. And you're going to see here that you can prove it using Mohr circle. And here's Mohr circle. This is the way that you do it with Mohr circle. This is the way that you draw the 2 points. You have 2 points for the stresses. And this gives you the principal stress, which means that you have no shear at all. You're going to have only diagonal tension. So look at what happened here. This is giving the amount of shear that you started with at each point. And then at the end, this is going to be sigma 1 and sigma 2, at which you have no shear at all. And this is going to be the direction of the diagonal tension. All right. In beams, if you have homogeneous beam, like wood, like steel, and you take 2 stress elements here, A1 and A2, look what happened. On the top, you are going to have compression. On the bottom, you are going to have tension. We understand that. And the actual bending stress distribution is going to look like this. Compression on the top, tension at the bottom. Since I'm gonna have this conjugate shear, so for each vertical shear, I need to have also horizontal shear coming this way. I said, okay, now I understand this because of equilibrium. Now the big question is gonna happen when you go on the top of the beam or right there at the bottom of the beam. What's gonna happen? Do you expect that you're gonna have a shear stresses in the horizontal direction at this point all the way at the bottom or on the top of the beam? Are you saying if I'm gonna be standing here below one beam and I'm able to touch the beam from the bottom of it, do you think some force is gonna be taking my finger and move it right or left because I'm gonna have some shear stresses in this direction? I'm gonna say no. At the free end here, there's no way that you're gonna be seeing any shear stresses. So the shear stress that we're talking about when you take the total shear divided by the cross-section area, was just like an average shear. But in reality, shear distribution is gonna look like this. As you see here at the bottom, fibers of the beam, the shear stress is going to be completely equal to 0. There's no shear stress here. And your stress element in this case, you need to take an extremely small element, and at that point on the top, the shear stress in both directions, in the vertical, horizontal, is going to be equal to 0. But once you go down, right in the middle, it's going to be equal to the maximum value. Again, this is going to be like more circle. You're taking here one stress element, you have tension, and then you have shear. You try to draw this, and then you figure out the more circle, and then you find out direction for the diagonal shear, diagonal tension, which is going to be on one of the same. Okay. Do we have equations for those homogeneous shear? I'm going to say yes. For the flexural stress, we understand this equation that we have used already in this course earlier. It's going to be the moment divided by the moment of inertia multiplied by C when you have a homogeneous section. But when it comes to shear stress, the shear stress is going to be equal to the total shear force. So I'm going to say this is going to be shear force, V uppercase, then multiplied by Q, which is the first moment of area at the section that you're interested in. I is going to be moment of inertia. And B is going to be the section width at the location at which you are trying to find out here the shear stress. And this is going to be the principal stresses, again, from Mohr circle. And then after that, we'd like here to see how can we design for shear. In order for you to design for shear, you need to follow this load combinations. If you have dead load and live load, we're going to be doing exactly the same thing, like what we have done here in flexure. It's going to be 1.2 shear due to dead load plus 1.6 live load due to the live load shear. And then you compare it with 1.4 times D. And of course, you take the larger of the two combinations. In conventional beams, reinforced concrete beams, we say that phi-Vn, which is the total shear strength of the beam, is going to be equal to phi. This is going to be what? The reduction factor, stress reduction factor, multiplied by the concrete contribution and the steel contribution. Concrete contribution is going to be given by this equation, 2 square root of V prime C BW times D. And for the steel, we have another equation for it. The equation for the steel says that here Vs is going to be equal to AV, which means the tie cross-section area, multiplied by D divided by S, multiplied also by F sub Y, which is this equation here. AV, cross-section area for the ties, multiplied by the length for the ties, times D divided by S, which is the spacing. Do you guys recall this information? Did you guys seen it recently?
Yes, sir.
Okay, excellent. The phi factor for the shear is going to be equal to 0.75. Now, in this case here, for conventional concrete, there is no axial load on the beam. You guys know this, right? Beams usually support moment. So the shear strength here, it is based on two components. The steel component, which means the ties. When you put ties there, the ties are going to be taking this tension force, as we understand. But also there is this concrete component that you should not ignore. And when it comes to concrete component, is actually based on the interlocking between the aggregate. Which means if you just put sand in the beam, just imagine that you put sand in the concrete beam, the beam is going to be very weak in shear. because there is no friction, there is no internal friction. It's going to be very loose. So you need to put a mix, and this mix is going to be what? It's going to be with different side of the aggregate. You're going to have your fine aggregate, coarse aggregate, and even the coarse aggregate itself is going to be graded. You cannot just have them all of one size. And the reason that you do this because you'd like to see this interlocking between the aggregate particles. Meaning, if the aggregates, if there's not enough connection between the aggregate particles, if there's no interlocking, you're going to lose the shear strength due to concrete. The steel strength is going to be there, but this one is going to drop a lot, which is going to be a big beam, right? So I have here two cases, or actually I can say here three cases. One beam, no tension or compression. It's going to be beam number one. This is going to be the main beam. Another beam, I'm going to put compression on it. The third beam, I'm going to put tension. So the one with no tension and compression, it has a strength of 2 square root of A prime C times the cross-section area of the beam. So I'm wondering about the one in tension. Do you think the one in tension is going to have the same strength and shear? Don't forget, it's about interlocking. I'm going to put the concrete beam under tension. Would I lose some of the shear strength or I wouldn't?
Yes, you would.
How about in compression?
No. It would probably raise.
So you think that the compression is going to increase the strength and shear?
Yes.
Okay, very good. So what happened in pre-stressed beams? Do we have compression or tension on the beam itself? In pre-stressed beam, what do we do? We draw this for quick. You say, okay, here's the beam, right? And to do pre-stressed beam, I'm gonna do this. What is this? This is gonna be compression. Not just one compression, I'm gonna put here 2 compressive forces. This is how we produce pre-stressed beams. So in pre-stressed beams, I'm gonna have compression on the beam, which means I'm expecting the shear strength due to concrete in pre-stressed beams is gonna be higher than that for conventional concrete. So this number here is gonna be going up for pre-stressed beams. This can be also a very good question, like true and false. When you add here pre-stress, when you add the pre-stressing force to a beam, would the shear strength increase or reduce? I say shear strength is going to increase. Why? Because once you put compression, you are bringing all the aggregate, and the interlocking is going to increase between the aggregate particles. Meaning, in pre-stress, I'm expecting shear factor to be slightly higher than this. So this is good here for conventional concrete, right? For beams and everything, and slabs and whatever. But once it comes to pre-stress, this needs to change. But how about VS? Let me look at the equation. VS is not really, I don't see here any good reason to add strength due to steel if you have pre-stress. But I see here a very good reason to increase this value because interlocking is going to increase. Just imagine that you bring here 2 hands. You have here 2 hands, right? And you don't put any pressure on your hand. And you just keep it very light. Now you start to bring it up and down like in shear. Very easy, right? They slide easy. But if you put compression now, try to push it up or down. Now you tell me what's happening once you start to put pressure. And I say, well, this is unlike concrete beams. I'm going to say yes, but now you increase the friction factor or the friction force between the 2 hands. So this pressure, you're adding more friction between the particles or between the 2 surfaces, between the hands. Now it's going to be tough to move them, which means you're going to be gaining here some shear resistance. So now it makes sense to me that adding compression on the beam like pre-stress is going to increase what? Is going to increase the shear resistance of this beam. We have here some equations that I'm sure that you have gone through it already in concrete 1, in the first concrete design. And then also you need to be sure that once you put a tie here that you need to hook it around the top and bottom bars. So here, if you put bars. You cannot just put the tile without bars. Otherwise, it's not going to be doing anything, right? Top and bottom. Like what you have also here in this picture. You need to have rebars top and bottom. Otherwise, the tile is not really doing anything when it comes to the shear strength. We have here one example. This conventional concrete design. And I guess I'm gonna stop at this point. I'll let you guys go. But please, I want you to read this example one. It is a simple example in shear design that you guys have seen before, or maybe you have taken it exactly same, or maybe, yeah, I mean, you have studied shear design before for beams. So please, I want you to finish this before we come for next time. So next time is gonna be only a few slides here to complete our business. All right? Any questions?
No.
All right.
Good, thank you.
All right, thank you. You guys have a good night.
Thank you, Professor. Take care.
Thanks. You too. Okay, bye.